One new unit, we're going to talk about the accumulation of change, but more commonly you'll hear it as area under the curve. So just to read along with it, the region between a function and the x-axis is called the area under the curve. Under in this instance does not mean below, which is confusing. It means between the x-axis and the function. So for example, if we look at these different functions, what we want to do is we want to shade under the curve, which means shade between the function and the x-axis. So here our x-axis is here, so we're going to shade right here. This one is where it starts to get confusing because we're actually shading above the curve, but it's still between the curve and the x-axis. Right, so that's the key part, is the x-axis. Right, see right here. And then the final one is even a little trickier. There's portions that are below and there's portions that are above the x-axis. So we're going to shade both of them. So it's always, you know, the area between the x-axis and the graph, the function. Okay, so let's take the rate of change function and examine its graph. The area under the curve gives us the accumulation of change. So what does that mean? It means we can find the total amount of something by looking at the area under a graph. Okay, so you are on a road trip and your car is on cruise control for 4 hours, which usually wouldn't happen because someone's going to slow down in front of you. You travel at 60 miles per hour. How far have you traveled? So even before you knew what calculus was, you could probably solve this. You would just do 60 miles per hour times 4 hours, and that would give you 240 miles. Oop. Right, because the hours cancel out, and so we're left with 240 miles. So you had a nice little road trip. That's if you're driving at a consistent speed. So the way that we do it with calculus and graphs is you actually want to use the area under the curve. So if we were to try and find the area under the curve, we know we're going to 4 hours. So we're going to find the area of this shaded part right here, because this is our x-axis, just to remind you, and then our graph is that solid line above. So if we're going to find the area of that, we would do 4, right, the area of a rectangle is length times width, which hopefully you remember. So our length is going to be 4 hours times our width is 60 miles per hour, and clearly we get the same answer, 240 miles. So something key to note is that we need a rate of change function. So that means our y-axis has to be like a rate of change, right? So we have rate of change. We have like miles per hour over here. So this needs to be miles per hour. If this was just miles, then it wouldn't work. So you need to have a rate of change as your y-axis. Okay, so our units are actually sort of nice here. The dependent unit multiplied by the independent unit, right? That sounds gross. In other words, it's the unit for y times x. Very nice. Right? So miles per hour times hours, that cancels out. We're just left with miles. So this is what you should see a lot in these types of problems. Okay, so let's look at an example that's a little more complicated. So we know right away that we can do our area under the curve because this is a rate, right? And it tells us, it says it's a rate. So we know we can do it, right? Because up here we said we needed a rate of change. Okay, so the graph below represents the rate at which water is leaking out of a tank. The units are given in the graph. How much water has leaked out of the tank after 9 minutes, right? So you don't need to draw this, but right, we have this tank. I don't know, there's like a hole in something and water is leaking out, right? Bad news. Or, you know, maybe they want it to leak out. Maybe it's supposed to leak out. So if we were to look at this, right, At first it's leaking out 2 gallons per minute, and then it's slow, it's increasing sort of fast, and then it sort of slows down the increase to 4 gallons per minute. Then it decreases, and then it goes back to 2 gallons per minute, and then it slowly stops, right? So maybe someone had a hole, they made it a little bigger, they tried to make it a little smaller, and then they sealed the hole, right? So that's what's happening like in the real world. Let's think of the numbers. What we need to do is we need to find the area. So when you have shapes like this, you actually want to break it up into like little puzzles. So remember, this is our x-axis right here. So we're trying to get this weird shape. So we're going to make a puzzle piece here. Actually, sorry. We're going to make this rectangle. We're going to have this circle. And we're going to have this triangle. I mean, you could break it into 2, but it's easier just to do the rectangle. Okay, so for this rectangle, we have 6 times 2 equals 12. For this triangle, you want to remember a triangle is 1/2 base times height. So we have 1/2 times, so this is 1, 2, 3, 3, and then 2. So that just equals 3. And then some of you may have forgotten the area of a circle, but hopefully not. Area of a circle is pi r squared, and r is our radius. So if we look here, if we were to have the whole circle, we'd see that the radius is 2, right? It's half of it. So r equals 2, so we have pi times 2 squared, which is 4 pi. But if you notice, this is half of a circle, so we need to make this half. So the area of this section right here is 2 pi. All right, so like my star student said, we're going to add these up. So we have 12 plus 3 plus 2 pi. We can just write this as 15 plus 2 pi. We don't need to write it in decimals, but you can. And then our unit is gallons, right? Because we take gallons per minute times minute. The minutes cancel. We're left with just gallons. So if you were talking to your claims adjuster on the insurance and you're like, oh, I had 15 plus 2 pi gallons of water leak out and destroy my basement. And they'll be like, thank you for that. So just to recap, before when we were thinking about this graph, this was telling us the rate, right? It was like, okay, at time 1, it's losing 2 gallons per minute. At time 4, it's losing 4 gallons per minute. At time 7, it's losing, 1.3 gallons per minute, which is helpful, but it's also helpful to be able to answer, like, how many gallons did I lose in total? Does that make sense? Let's do a trick question or like a reach question. How much water has leaked out of the tank after 6 minutes? See if you can answer that. 12 plus 2 pi gallons. Very nice. Yeah, 12 plus 2 pi gallons. Yeah. 12 plus 2 pi gallons. Very nice. Just add these 2 portions. All right. One last example problem, and then you're done, so not so bad. Okay, so a particle is moving along the x-axis as a rate modeled by RT, which is good. Remember, we said we always want rates. And shown in the graph below. And then it's asking us, how far is the particle from its starting position at certain points of time? So if we think about this, right, we have our x-axis, and we have this particle, right, this little guy. And he's moving back and forth, right? He's moving either this way on the x-axis, he's like sort of bouncing back and forth. So if we look at this graph, he's moving in a positive direction, and then he's turning around and moving in the negative direction, and then at 8, he's moving back in the positive direction. So if you think about it, he's moving in the positive direction, but he's slowing down, right? So he's like moving really fast, and then he's slowing down. But he's still moving forward. But then at 2, he's like building up speed. He's like moving faster in the negative. He stays at this negative 15 centimeters per second. and then he pretty rapidly, or pretty slowly, he's going from like 15 to 0 pretty quick. So then he goes back. So this is sort of hard to conceptualize, but just think like he's going positive, he's going forward, backward, forward, but this is like the speed, right? So at here, he's moving faster than here, but he's still moving in that forward direction. Again, this takes a little bit of time as you go through the practice problems. Hopefully you get the concept. But let's do our area, right? So it's saying how far is the particle from its starting position after 10 seconds? So we have all these shapes, and we're going to break them down and try and find the areas for them. So we have this triangle here. We have this piece here, which is comprised of a triangle, a rectangle, and a triangle. And then we have another triangle here. So if we look at this one right here, we know that it's 2 times 10 divided by 2. So we have, right, we have 1/2 base times height. So we have 1/2 times 2 times 10. So be careful with the units, right? The height isn't 2, the height is 10. All right? So this piece here equals 10. And then I want you to take the time to try and figure out the rest of the pieces. So I'm going to pause the video. All right, so if we look at this triangle right here, we should get 1, 2, 3. So 1/2 times 3 times 15, which is 22.5. This rectangle right here, we have 2 times 15, which is 30. Here we have 1/2 times 1 times 15. So that's 7.5. And then finally here, we can see that it's the same shape as the other one, so I'm just going to label it 10 without calculating it, because it's like 2 across and then the 10 up, right? Okay, so how far is a particle from its starting point after 10 seconds? So if we are this particle, so after 2 seconds, we move 10 to the right, right? And then after from 2 to 8 seconds, we now are moving all this but to the left. So this is all 60, right? So we moved 10 and then another 50. So now we're here. And then after this part, we move forward 10 again. So hopefully that makes sense, right? If I was to draw this, right, we started here, we went here, and then we went all the way back, and then we went back, right? But we're on the x-axis, so we're not moving up and down at all. I'm just drawing this line so you can sort of see like how you double cross you like crossed over your path again, right? So for this, we have to remember that this down here is negative numbers. So that's the trick with this question. So we have positive 10, minus 60, and then another positive 10. So we're actually left with negative 40, and the answer to that would be 40 centimeters to the left. Right? So if I started here, I finished here, and I'm 40 centimeters to the left after all that traveling. So if you're thinking about from 2 to 8, right? So this was where I was at 2. 2 seconds, 0 seconds, 8 seconds, and then 10 seconds. If I was at 2 seconds, 2 to 8, I actually moved negative 60, which would be 60 centimeters to the left. So that's it for this lesson. It's a lot of geometry, and then sort of like spatial awareness, like trying to understand what's happening, like visually in your head. You can do it without that, but it's helpful to try and think about like how people are, like imagine if you're just like walking on a path, and then you like had to go back and get something, and then you like start walking forward again. So trying to think of all these different scenarios, like the water leaking one, like trying to think about what it means in the real world, right? Like, okay, this one, it tells me the rate of gallons leaking, but like I'm trying to find how much water actually, you know, came out. So these problems aren't so hard. It's just a matter of remembering your geometry, breaking down those shapes, and then making sure you conceptually can answer the questions, because they're asking for They're asking for like real world answers, not just like numbers, right? They want to say like 40 centimeters on the left, not just negative 40. So, not too bad of a lesson. Hopefully you agree. Oh, what happened?